Hello, Professor Sargent here with you again. We're going to take a look at walking through some problems regarding the normal approximation to binomial probabilities. Now, first off, before getting into some examples, you need to recall that for a binomial random variable, the mean of that variable is equal to the number of trials, little n, times the probability of success, little p. And sigma, the standard deviation for that binomial random variable, you'll have the n times p again, also multiplied by the probability of failure, and then you take the square root. Remember the probability of failure being 1 minus p, because in binomial experiments, there are only two possible outcomes, and they are mutually exclusive. Together, their union forms the entire universe, your universal set or your sample space if we're using probability language. Now, to do the normal approximation, you're going to see different authors say some different things, but for the course that I'm currently making this for, besides the fact that you have to have a binomial experiment, you wouldn't want to use a normal approximation to a binomial experiment if the experiment was not binomial to begin with. We need the variance. What you get just before you take the square root here to get the standard deviation, the variance has to be greater than or equal to 10. So we're about to take a look at an example. We're given a binomial situation where the number of trials is 54, n equals 54. Probability of success is 0.6. And we want to approximate the probability that x equals 39. In fact, what we're going to do is find this two ways. Either use the formula for binomial probability, or we can use binomial PDF. And then following that, we're going to approximate with the normal distribution if these conditions I wrote back here apply. All right, so using the formula, we would have NCR, so 54, choose 39. Times probability of success is 0.6 raised to the 39th power, that's how many successes we want, times the probability of failure, which technically I could find out that that's 0.4. It's not such a bad number. And you need those parentheses there if you're going to do that. And finally, the number of failures would be 54 minus 39, which should be 15. But particularly on the older calculators, you might want parentheses around this as well. 54 minus 39, whether that's 15 or not. When rounding to 4 places, the 10,000th place, this is giving us 0.0207. Now, if we had used one of the distributions, because that's for one value of x, we would go to binomial PDF. Think of that one value as a point. And again, there were 54 trials. Probability of success was 0.6. And we wanted the x value or r value, whatever, to be 39. If you're one of my students, you would want to write down what command was used, what you plugged in where, and then give that answer rounded to 4 places. And we can see it's coming up with the same thing. Now, next we need to check whether or not we have the variance greater than or equal to 10. Oh, wrong key there. So n times p, 54 times 0.6, that's our mean. And I'm going to write that down over here. 32.4 for mu. Multiplying that by 1 minus p. Again, p equaling 0.6, that's not such a bad number. We could multiply that answer by 0.4, but sometimes the numbers aren't always as nice. Either way, same thing. So the variance is 12.96, and that is greater than or equal to 10. So it is legitimate, since this is a binomial experiment, to use the normal approximation because this holds true. And our standard deviation is just going to be the square root of that 12.96. If you're not asked to express that as a decimal, then we can leave it like that. I want you to resist the urge to round whenever you like at whatever step to whatever place. All right, so going back, let's see here. Going back to our question here. We do have that n times p times the quantity 1 minus p is greater than or equal to 10. So yes, we can use the normal distribution to approximate this probability. Now, we have a number of options for computing this, either using z-scores or tables. And I'm going to show all of those in this example. But first, we have to apply the continuity correction. So since x is equal to 39, which is a little bit above our mean, we wanted the probability that x was exactly equal to 39. And the area of a line segment, since a line segment is one-dimensional, it has no area. Area measures things that are two-dimensional. So we do the continuity correction. Go half a unit left and a half a unit right of that raw score x. So that we will capture that region that we want within this region. All right, so if we go with the most old school approach, we're going to need the z-scores for when x is 38.5 and when it is 39.5. Remember, this is our formula for z-score, and we specifically have found out what mu and sigma are equal to. So I'm going to show on the calculator plugging in 38.5 and 39.5 for x. Remember to put parentheses around the subtraction in the numerator. 38.5 minus that mean of 32.4 divided by whatever sigma is. We left it at square roots of 12.96. So to the nearest hundredth, I'm coming up with 1.69. And then change the 38.5 to the 39.5. And that to the nearest hundredth, 2 places, is 1.97. So I could look this up on a table. Our 1.97 is right here, 0.9756. Back to the left of that, we have an area of 0.9756. Double checking that. Yep. Whereas back to the left of the z-score 1.69, we have 0.9545. So I'm going to take away the unshaded extra part right here and subtract 0.9756 minus 0.9545. See what that looks like. Again, subtracting 0.9756 minus 0.9545, taking away that extra unshaded part. All right, here we go. .9756 minus 0.9545. Oh, I think I got that. Yeah, 0.9545. Okay. Point. Coming up with 0.0211. Let's see what's going on here. It's kind of close to what we came up with exactly. They're happy with that. And the previous answer was 0.0207. So this is 4 10,000ths away. Before going on to something else though, I want to show you another option. So that would be under our distributions here. Go to normal CDF and without needing the z-scores, we would be going 38.5 to 39.5. We don't need the z-scores because we've got the mean of 32.4 and the standard deviation being the square roots of 12.96. And when rounding that would actually come up with 0.0208. And I'm not sure if the people that created the question at the online homework, if they would allow that 1/1000th of a difference between the two or not. It's a little tough to check into some of these things sometimes. Real quick, I'm going to show one more thing. If I go to graph y equals, and then into the distributions, Now let's turn off that plot up above, by the way, for the time being. Go. We go into the distributions, and for some reason pick normal CDF, sorry, normal PDF. Just give X as an X value, and then our mean was 32.4, and sigma was square root of 12.96. Paste that in there. Just going to try to graph this. However, we need to be very careful because our empirical rule tells us that 99.7% of our observations should be within 3 standard deviations of the mean. What I'm going to do is take that 32.4 and go 4 standard deviations, right? So 4 times whatever the square root of 12.96 is. And also go that far to the right. I'm going to do a little rounding, but I'm getting 18 exactly for lower bound and 47, well, 46.8. I'm going to round that to 47. So on my window, I'm going to change 18, 47. And if I left the X scale as 1, I'd see 29 tick marks. I don't want to see all that. So I'm going to divide that by 10. In the Y direction, remember that underneath the area of the entire curve between it and the horizontal axis, you should have an area of 1. So I've just spread that over almost 29 units. Technically, it goes on infinitely. So what I'm going to do is just try this out. I'm going to go a little bit below and a little bit above the x-axis, divided by approximately 1/30. I want to see if I'll see the peak. It's going just a little bit above. So I could try, say, going to 0.07. And this way, if I divide how far apart those are by 10, so that I don't get a lot of tick marks there. Still missed it by a bit. See if we can see it now. Still just missing it. I could have actually done something else to make this even more quick, but oh well. See about now. Still just missing it. Alrighty, let's see here. I'm going to pause this. All right, if I went up as high as 0.2, I was able to see it. See about 0.15. Okay, good. All right, so I want to be able to see below as well. So how about we go with negative 0.05? We don't need to go too far below the axis. Those y min and y max are 0.2 apart. So I'll divide that by 10 so I don't see a lot of tick marks. And there's a nice sketch. Now, what I wanted to show was if I go to second and above trace is calc and choose number 7, give a lower limit of 38.5. No z-score needed here. And 39.5 gives us a nice sketch. And it's giving us, when rounded, 0.0208 as well. All right, going to move on to another example.